And I see the great.
Well, let's get started. It's a great pleasure to have here Professor Dragana Ilic and Professor Angelika Kovacevic. They're both coming from the University of Belgrade in Serbia, and they're both experts in big data and AGN variability, and they're very involved in LSST preparations and in general the LSST AGN science collaboration. And today we're going to hear about algorithm development in preparation for the upcoming LSST data.
So, hello everyone. We are going to do a sort of unconventional presentation because we kind of arranged to talk both of us. And so I'll start and then we will kind of switch. And first of all, we would like to thank Maria for inviting us to this very wonderful city and facility. I mean, this is our first time here, and we are very much impressed with how big is this institute and the whole environment. And we are looking forward to continuing some collaborations between this institute and our institute. So we come from the University of Belgrade, Faculty of Mathematics, Department of Astronomy, and are strongly collaborating with two important institutes in Serbia, which is the Astronomical Observatory and also University of Kragujevac, which is a very small university in Serbia. And here you can see several of our collaborators from our both from master students, undergraduate students, postdocs, and some seniors. So we are trying as well as like Maria here to build the group which is going to be dedicated to the well, several avenues of research, but recently in this moment, our focus, the biggest focus is on the survey astronomy, and especially Vera Rubin survey, which we will present shortly. So we would like to start, hopefully, with just which button should I press? Ah, here it is. Okay. Oh, okay. But that was the preview. So most of you, and especially we in Serbia and in the rest of the world, were absolutely grateful to a lot of survey astronomy, which started several decades ago. And one of the example surveys here, the Sloan Digital Sky Survey, which kind of opened the horizons in both, of course, mainly in the optical band, but in the photometry and spectroscopy. And really, what I really want to emphasize, the SDSS survey was crucial for the democratization of astronomy and of this open science format, and that really helped teams all over the world to kind of reach the top level league when it comes to scientific research, and especially for us in Serbia, which is a super small community, much smaller than here in Greece. That survey like this really opened the space, and it was a sort of a ticket for us to join the many research collaborations. And just for a preview, this is one image from the SDSS combined GRI bands, a very small field of view reaching the magnitude of 2022. And this is a real observation of the same field, which will come in a second, of the same field achieved with the Subaru telescope, so 8-meter class telescope, which is the same one as the LSST will build. It's stuck. Yeah, it is stuck. I'm sorry. No, wait, maybe it takes some time. Well, I don't understand why it takes some time. This is just a slide.
It worked before.
Yeah, it worked before.
But the problem is actually Zoom. That is.
Yeah, we didn't know about the Zoom, and then we would arrange for a different setup. Sorry. Apologies for everyone, also on the people on Zoom and those who are watching the recordings. But
No, we are stuck. I'm sorry.
Let go a few minutes. Now it's kind of probably has some.
Probably exit the presentation.
But if we do this,
We manage.
there's some also chat.
I'm sorry, we should actually, we will stop this presentation on the Zoom and we will go without Zoom.
Shall I? What shall I do? I mean, here it is. Okay. Let's hope for the best. I mean, it's.
And don't hide anything.
No, this is this. Okay. So maybe it's better if you just like don't do this, but do this.
Okay.
Okay. So the same field of view. Now, I mean, the whole excitement is kind of it's spoiled, but it doesn't really matter. So we reach with the LSST 27 magnitude of is complete, which is in the next 10 years, but it doesn't really matter. We are starting as we speak now. And the whole sky, the whole parameter space, which will be opened with this survey when it comes to the depth and in terms of the distance and the magnitude of the object is completely different. And we will basically increase the number of objects in the galaxy and especially active galactic nuclei, which we are here mainly interested in. So just a brief idea of the Rubin Observatory. So it is now the whole construction is completed. All the major setups, all the major parts are being installed. So the last one was the biggest ever digital camera, the CCD, which is the size of the small car. These are the photos of the installment of the last piece, which was this camera. On the telescope which hosts the mirror of 8.4 size, 8 meter in size. And the last, let's say the days as we speak, these are last commissioning phase of the camera, and the survey is still about to start in a month from now. And the survey, the legacy survey of space and time of the Rubin Observatory, which you see here, is going to be basically a 10-year-long survey, which will produce really a big data and a movie of the whole sky visible from Chile. And as I said, it's going to open a completely new parameter space because we will have billions of new stars and galaxies and millions of new quasars. So the whole the announcement of the start of the survey is happening really soon, in a month from now. So it's now set that on June 23rd there's going to be a first look watch party. It's going to be a public media event, so you are all more invited to join and to host the party here as well. Yeah, you should do that. And the most important thing is that after this first look watch party, where basically as they announced, the best ever images of the universe will be revealed, what will become available is what is announced as data preview 1. It's basically science grade data obtained with the commissioning camp. The commissioning camp is basically, commissioning camera is a smaller version, so downgraded version of the big camera. So we will have about 2 months of data. So also the variability and the light curves of the first images for the community to test. So basically, even though the survey is just about to start, we already have a preview data to test our algorithms and to, let's say, enroll into the investigation. So check out all the details about the data preview 1, which is going to be available right after the first look watch party. What for us is the most exciting, and what is one niche that is quite amazing for the AGN study, for the some object study, is the study of the nuclear activity in galaxies. So this is just a slide as an introductory about the basic properties of the nuclear activity in galaxies, starting from our own local universe, from the Sagittarius A stars up to redshift of 10. We can study the activities in the center of galaxies. And what is really amazing and now heavily accepted by the large community is that basically most, if not all, galaxies host a supermassive black hole in the center. So the study of the processes happening in the galaxies centers are really important to understand the processes in general in galaxy formation and evolution. So this nuclear activity is quite a ubiquitous phenomenon in all galaxies, and we know now, all the people who study nuclear activity, that there are so many various forms of activity in sense of we know that active galactic nuclei can come in the form of quasars, strong radio galaxies, blazars, which are heavily studied at this institute as well, so CIFRA galaxies and so on. And what is so peculiar about these objects is that they emit at all frequencies. Here is a sketch from M87, one of the most, let's say, studied AGN in all bands from optical, X-ray to radio. And what is really important that the study of this nuclear activity is basically reflecting all the processes which are happening in the immediate vicinity of the supermassive black holes. And what we know now is that we indeed have a supermassive black hole in these objects, and this is of course the Event Horizon telescope image of a supermassive black hole in M87, which was basically the proof that we indeed have a supermassive black hole in galaxy centers. So what is so peculiar about AGNs is that they are, let's say, a quite exciting object to study in the sense that they are completely, let's say, different from the normal galaxies in the sense that they are having a sort of radiation mechanisms across the whole electromagnetic bands, and they show different observable properties from strong emission lines, variability, polarization, radio emission, and so on. And in most AGNs, you actually see these key observable properties, which are the result of different, let's say, radiation processes from different, basically powered by the accretion onto the supermassive black hole, but these processes are causing several other physical mechanisms across the AGN, coming from both the accretion disk, the jet launching, and the whole interaction with the host galaxy. And what is really incredible is how we actually can study these objects. So one way we can do a survey study, which was the SDSS survey was one of the first one to study this on massive scales. But what is really important when it comes to AGN are these multi-wavelength campaigns in terms of both, let's say, individual objects in terms of one epoch observation, but moreover in the time domain aspects, because what we know about AGN is that they are varying on different time scales and across the whole electromagnetic bands. So in general, we are mostly focused and mostly interested in the optical band. And what is the biggest challenge actually here, and we want to really emphasize this, that basically we cannot spatially resolve this object unless using the Event Horizon telescopes or other interferometry missions like Gravity Plus installed on the VLT. So what we actually aim is to resolve this AGN in either time, like with these light curves, and then study those properties, or in energy and get the whole multi-wavelength bands. But studying getting the simultaneous observations across the whole electromagnetic band is the challenge that I'm not aware that has been solved, because in order to synchronize different facilities to observe the single object at the same time is very difficult. And we have an example of AGN Storm campaign, which we collaborated together with Ethan on that, which combined massive groups across the world, across the globe, and it was a huge effort to combine all of these facilities to monitor an object, and it was for 2 objects basically that we achieved this. So for massive surveys, like for example, for the LSST, which will produce millions of these light curves, we need to think of different strategy, how to extract information for this kind of light curve. And what is the biggest challenge is that all of these signatures of variability are having, let's say, different properties across the electromagnetic band, which is illustrated here. For example, going from the X-ray up to the near infrared, you will see that the variability scales are actually different, which reflects that this variability is coming from different parts of an AGN. And just as a sort of a reminder, I kind of realized that I haven't even mentioned the whole structure of an AGN, even though it was illustrated here. But the whole region, what we manage by basically combined multivalent and variability studies, is to resolve this kind of very complex structure by just studying signals like this, that we have a supermassive black hole, accretion disk, an X-ray emitting corona of so far unknown geometry, radio jets, and different emitting line regions coming from the broad line region. And then we have the further out, the narrow line region, and we have this obscuring material of some sort of dust content. So what we wanted to basically emphasize here in the optical band, there are really a lot of interesting features when we look at the optical spectra. There is very rich emission and absorption line spectra. We see a lot of interesting morphologies which might produce some of these emission and absorption lines coming from either an complex motion of these line emitting clouds like winds and outflows. But what is also very much interesting for us and the community here, whether we can have signs of galaxy interaction, or even some remnants of the galaxy interaction, like that we have a binary supermassive black hole present in this galaxy centers, which is expected as a sort of a final stage of galaxy interaction and merger. So what is the challenge when you take a look at these light curves that we observe them? The physics behind the light curves is very complex. So here is just an illustration of some possible, let's say, physical processes that can be behind can happen in the plasma present in an AGN, which are producing a signal that is very much, let's say, burdened with a different level of noises, either starting from the, let's say, the instrumental noise from the photometric observations, then the stochastic process is happening in the accretion flow, which are producing the red noise, and then different, let's say, additional mechanisms, like we may have some periodic behavior due to some binary presence or some periodic accretion. We may have a gravitational microlensings and so on. So it's a very complex physics, but what we basically have is a single light curve, and our aim is to disentangle these different contributions and try to conclude what is physics there and possibly discover these, for example, exciting events, either a binary supermassive black hole or some transient events. I heard people talking here about the tidal disruption events, which are one of the most also exciting phenomenon to be discovered as well with the LSST. So what are the challenges when it comes to the Rubin infrastructure in this time domain aspect is that we are going to have another level of data in the sense of the discovery space. So the Rubin is going to, as you have seen in my first slides when we wanted to show what the Rubin will see, we will observe much more new objects. From the asteroids all the way up to the AGN. And what is important, and this is a variability tree, that the light curves that we will discover will come from a variety of objects, and our tools, what we are developing, are trying to classify and characterize the light curves and help in characterizing the AGNs, but as well maybe applied to light curves of stars and even asteroids if we have some, let's say, periodic observation and so on. And this is let's say the place to introduce our team is this, because you all know that the LSST is the NSF and DOE, Department of Energy mission. So it's a US funded mission. So where are the whole, let's say, international teams and what is our part there? And this is what basically happened 5 years ago, is that LSST opened the call for the international teams to join with their expertise and submit different in-kind contributions, either from the software development, which is one of our in-kind contribution, to the facility support, like follow-up, computational centers, and so on. So our in-kind contribution has been reviewed on several stages, coming from the LSST experts all the way up to the NSF, and has been approved and accepted. It is called the Serbian AGN group, and this is this SERSAG acronym, which is very long. So we are an official in-kind contribution to the LSST offered by the University of Belgrade and Astronomical Observatory, which has basically two main contributions. One is the directable software contribution. Anđelka Kovačev is the contribution lead. And the other one is the follow-up facility with the Milankovic 1.4 meter optical telescope at the southern Serbia. And I want to emphasize this here for the community here. It might be interesting to combine and to synergize efforts, and especially because I know here you have as well facilities that might be offered to the LSST as some follow-up for some follow-up activities, because both you and we here in Serbia are located geographically quite conveniently for the rapid follow-ups of some of the most exciting events that LSST will discover. So now I would like to invite Anđelka to continue with presenting the in-kind contribution. And before that, just I have another statement that said that we have in January, basically 5 years after the whole evaluation, signed finally the data rights agreement with the LSST, and which kind of announced officially our contribution. So, Anđelka,
thank you so very much. How much of the time I have? Just not
25 minutes.
Okay, thank you so very much. It is great honor for us, because Maria, who invited us, is the leading worldwide expert in supermassive binary black holes, with all wonderful young people joining her team. And it is great honor for us to be here. Also great honor because Greece is the cradle of the democracy and European civilization. But most of all, the Princess Catherine, who is married to our king, Alexander Karageorgievich is Greek princess. So it is multiple honor for us to be here. Okay, so related to the to our in-kind contribution, here we will see some administrative milestones and some actually the contribution. So we have two packages. As you can see here, we have the latest version of Quasar Harmonic Explorer, which was released with continuous integration and deployment pipelines, fully passing, and it is submitted to the Journal of Open Science Software. On the other hand, we have the other software that we call Quasar Neural Processes, which comes in two flavors that is actually related to recovery of the light curves. And actually we have upgrade of the conditional neural process that is called attentive latent neural process, or QNPy latte, for modeling of the light curves, transfer functions, which was recently released. It is interesting that we are among the first teams applying the neural processes for the recovering of the light curves, and we will see that they are actually some kind of the combo between the neural networks and Gaussian processes. So that is the kind of the probabilistic modeling. As for both of these softwares, we can say actually that QNPy Quasar in time domain, we have actually 4 axes. Here are only 3 axes. So we will follow the variability of the brightness of the objects that can be also seen in the spectra, which will also affect the shapes, either of the orbits or what we can expect in the object. So we can say that QNPy actually is something that is related to recover the shape of the brightness variation, which can also help us to detect some shapes that can be encoded in the light curves, what we can expect, for example, eccentricity and the supermassive binary black holes. From the other side, we have Quasar Harmonic Explorer that is actually, this is like projector, but this is some kind of the extractor of possible multi-periodic signals. So with this, if we would like to position our softwares, they actually these software are actually within this hub that is actually related to detection of some kind of temporal time scales, actually in the AGNs, and it is some interrelated hub between what we can expect from the observables in the AGNs and also bridging with respect to the population level scaling. So if we have software that can operate on the large amount of the data, we can actually support not only individual objects but also the population level scale software. Scaling laws. And such scaling laws, we already have some precursor analysis, like in Vincenzo Petreca, that was released within the AGN Science Collaboration last year. So actually, both of these software should support community and cooperate with other software, which are actually somewhere here, which we believe that is also for most of these ideas that are coming now, that we can have in deep learning, machine learning. We have maybe several avenues, but here are 2 according to the Ashish Mahbal, one of the famous persons for devising ZTF facility softwares and new methodologies. We have some traditional deep learning, which means that if we have the light curves, two-dimensional data, that we are going into the extraction of statistical features that can be, more, how to say, coarse, not fine, and then to proceed into what we want with deep learning. However, there is another avenue, and we would like that our software be in this avenue so that we can not only use standard statistical features, but on top of that, that we have some new type of the latent or other type of the features. So here we can see actually projection of the simple light curve into two-dimensional heat map. That is what we have, and we can see actually that this heat map can be seen as the differential version, as the descriptor of the velocity of the variability within the light curves. As for our, as I said, both of our software actually should go and support community efforts by introducing new types of the phase space, like in the sense of the extractor of the harmonic oscillators or oscillations, or actually provide new type of the latent space, which is actually context aware in difference to variation autoencoders, which actually encode the whole light curve. Here we are context aware, and that is what is in the line with Rubin community, that we need methods of separation and clustering in different various phase spaces. And we will see that harmonic extractor is actually introducing two-dimensional period phase space. Both of the codes are actually implemented on various platforms, also in-house platform like small HPCs, or on some bigger artificial intelligence platform of our government. And here we can see some examples of the execution time for statistical significance. That is, for example, because we will see wavelet transforms, independence of the type of the light curve. We can have either, execution time needed for example, for 2 million objects between 32 days up to 106 days per Rubin year. And here are some tests that we will see some tests. This is the Quasar neural process with attentive latent space. We tested this on the LSST AGN data challenge, mostly based on the SDSS data, also on some of Gaia quasars, then of some really interesting assassin quasar light curves, and on the ZTF that was actually constructed by Aman Raju, our international student. And we have two types of the neural processes that implemented. One is the conditional, the other is attentive latent. The conditional neural process actually aggregate the light curve points into single representation, and it is not temporally aware of what is happening. But here we are actually introducing the attention branch, so that we can actually extract more information, because we know that some correlation can appear on the points that are closer in time. And the reason is in introducing neural processes, because they are lightweight with respect to the neural networks that need millions of the light curves to be trained, and months of the computational power And the neural processes are actually something that is called meta-learners, in order that they can be seen like learning of the learned code. So that these are distributions of the functions on the data that can be modeled, and also they imitate some kind of the human logic, which means that you didn't need millions of snakes. It is just enough to see 2 snakes that you know that something is snake. So because of this, the authors of the QNPy, of the neural processes are actually needing this. And here is actually beyond only application of the neural process on the light curves. We also introduced for the first time in the quasars investigation stratification of the light curves using the unsupervised self-organizing map. Before modeling, we try to detect because not all light curves will be of the same topological characteristics. They will be different, and that was we were advised by our AI supervisor, Professor Mladen Nikolic, to try to find methodology to stratify light curves before application of the neural process, because that will speed up learning. So if I have millions of the light curves that are going like this or similar and train on them, and then I try to deploy that program on millions of light curves that have upward trend, then we will not have any meaningful results. So here is an example of how we can, we firstly apply the self-organizing map clustering, and then we try afterwards to train the code on these clusters, and we can immediately see what would be interested or not interested for us. The next, as I already mentioned, we try to deploy a quasar neural process on various prototypes for the LSST cadences, and we made ansatz that we cannot observe anything worse than of this type of the cadences. We see various kernel KDE's distributions of the cadences that we simulate, and here we can see actually recovery of the simulated light curves. Dots, black dots are actually the observations. Solid lines are the model, and importantly, we randomly choose context points to train the neural process. Difference with respect to the neural network are taking all points, but neural processes are just taking the number of the points we pointed to it. So it means that it is performing really okay with this on the quasar light curves. And also you can see the recovery of the transfer function, and the here are numerical results related to the recovery of the transfer functions and the light curves, and here is some results on the really adversarial example from the ZTF. On the other hand, related to the harmonic extractor, quasar harmonic extractor, here is just an example. Maria knows much better about this, what we can expect from the LSST on the fly of the 10 years of the observations, that we can have actually maybe some losses of the observations due to weather conditions, etc. And we can see actually the density of the objects, how they are actually moving across the phase space, which can be encoded in the optical light curves. So the optical time domain comes to the interest because of all of these 4 axes that I mentioned, that we can actually follow not only variability in the brightness, but also the position changing. And we can see that actually for massive objects, we will have a little bit restricted phase space for detection because, of course, of the upper limit of the periodicity detection. You can see comparison of the methods. This is our method of the Quasar harmonic explorer. All of the methods are transforming one-dimensional signal into, except the Lomskardo periodogram, which is staying into one dimension. Because we are going into the higher dimension, it means that we need more power, and that means that also wavelet transforms and our method need more computational power that we said. The innovation of our code is that actually we have this new type of the phase space, as I already said, period. Wavelet transform is time frequency, which is actually simplified on this in this map. Here we can detect on the surface. With the Fourier, we can detect on the surface waves, which can be actually squeezed or overlapped. But if we add the ultrasound detectors, we can actually take some plane of the possible oscillations vertically. But if I have the second source of the sound, then I can, if I cross-correlate those types of the wavelet transforms from two different positions, like two different light curves originating from two different positions with respect to the supermassive black hole, then I can maybe infer more texture, more information about the oscillations that we have. And how our methodology is working is explained here. We can uptake into extractor either the raw light curves, it can work with raw or modeled light curves, and this is the two-dimensional phase space of our method, where actually if these same oscillations are present in the light curve, they will be like cross-correlation islands on the main diagonal. Off-diagonal clusters perhaps can be detected in the TikTok signal objects that are close to the merger. And also we are capable to provide the numerical catalogs or even to innovatively present dynamical view of detected periods. Here, for example, logarithmic values of the IDs of the objects. Here are detected periods, and the size of the circles are relative error of detected periods by our methodology. And we also, for the detection of the periods, invented not only statistical methodology for detection of reliable periods, but also we introduced the intersection of the union of detected periods, where we have detected period, we have the relative error of detected period in the band, and then we can even, what we request from our objects in the LSST, that they have at least in two bands detected period. We are really strict, and then we can calculate the area of the overlapping. As much as it is overlapping, it is a higher level candidate, and we also implemented this robo-vector into all statistical significance detection. And here are actually the scheme of our software. And here is the example for on the Gaia. In the Gaia data, we have some interesting light curves with unnatural spikes that may be actually related to the facility itself. And then when removing the outliers for about 6,000 Gaia, that is actually done in cooperation with Professor Lovro in Institute of Ruđer Bošković, Croatia, we actually stratified the candidates based on on this data. And here is also some kind of the stratification that you can see in the live demo, that we can actually compare how they are actually detected candidates behave in various pairs of the bands. And just, okay. Also, we use the AGN data challenge light curves that they are really adversarial, and also ZTF, and try to inject the sinusoids in the real observed light curves. That is detected periods in the light curves without any injection. And here we injected the signals at the various amplitude level of the same 50 days period. And we can see as the amplitude of the signal is higher, it means that other periodicities will be attenuated. And we can see actually that our code can detect even such periods. And here are the papers that are submitted. Beside this, our methodology has been synergized with Lomskardo periodogram in the Fatovic et al. Publication dedicated to the follow-up campaign of the best candidate, of one of the best candidates for the binaries. And actually, in that paper, we use the spectroscopy from the Gemini, from the some other facility, and also implemented the modeling of the spectral lines with using the POSCI model by Popovic et al. From 2021, and try to fit the spectra with the binary model that can reproduce them. And also Dragana already mentioned importance of the follow-up. Dragana and Marta Fatovic are actually the leads for the AGN subgroup for the binary follow-up. And you can join that effort. Beside this, we have participated in the AGN Data Challenge classification contest, where our postdoc George Savic won the first prize together with Isidora Yankov and Iva Čvorović. And also we participated in the construction of the metrics for the AGN detection of the periodicity. So that is all. And I would like to thank you for your attention and time, and apologies for any glitch. Thank you.
Any questions?
Did we correctly written here?
Yes.
Okay, so my question is, have you let polarization into the yet?
Yes, yes, yes. That's not presented here, but we did. So yeah, apart from doing time domain studies on photometric, we did a lot of spectroscopic. I mean, that's one of our first, let's say, research was spectroscopic variability, and this is how we joined the AGN follow-up and the AGN storm campaigns. And then we are just learning how to do a spectroscopy, Fuhrman spectroscopy, which is the LSST with just 6 points. But what we have been involved was more like spectroscopic spectropolarimetry observations, which we did on a 6-meter telescope in a special astrophysical observatory in Caucasian. And we did there, they have a very nice instrument, Scorpio, for this. And we have been doing this to study the properties of the broadline region from the spectropolarimetry part in the type 1 AGN. And it's a very nice study which showed basically that there is independently basically that there is equatorial sort of Keplerian motion in the broadline region, and that the scattering was coming from a dusty region, which also was the equatorial. So that's one work we did. We also had several initiatives to try to introduce on Vidojevica, on this Milankovic telescope, to also install a small polarimeter for photometry. But our instrument is not very, let's say, it doesn't have an optical design which is convenient for. We did some tests with the very basic. I forgot what was I think we used the Savart plate or something like that. It was but it was not. We could not get something. But we were having some initiatives on that, and I know Luka Popovic was once visiting here, but maybe a long time ago. I don't know when was that, and had some initiative about this. But
so yes, we definitely have polarimetric light years. We have run several year programs
with the Robopol, yes.
And there is still a lot of unexplored content in these light years. We also have some high cadence data, but not much has been done with it. So I think it would be very interesting to talk about what we do.
Absolutely. So one of our, if I can answer this, one of our priority number one in all of this software that we are developing is testing on different light curves. And then exploring the avenue of what could be the next upgrade. Because as Angelica pointed out, for example, for this QNPy, we started just with the neural processes on light curves, and then we explored this in case of stellar light curves, and then we upgraded later on for adding this QNPy latte, where you could extract additional features from the light curve with just adding
yes,
additional.
And just to add that actually both of these packages are, even that we are calling them quasars, they are actually not limited to the quasars and can be applied to actually any type of the data. We had a PhD student from the biology who were doing something about the COVID, and even can model and impart the data. Also, importantly, all of these light curve, whatever electromagnetic wavelength can be actually used with this, and even to synergize, because we have various messengers, angelos, Greek language, so the photons, and so actually that is the main point. Software are independent of the wavelength, and even maybe we will try to apply QNPy on some kind of the modeling of the spectrum.
Yeah. So it was not only focused, one question first, sorry for us, and I'm very, and then we will leave for. So it's more, it goes beyond just strongly, let's say, radio loud objects, the study that you have, the monitoring that you have been done.
No, it's focused on radio loud object. Actually, not our guide was even more focused on gamma ray loud objects.
So it's very, but nevertheless,
but
I mean,
it's like it. So it's definitely quasar.
Yes, it doesn't matter, because, as I said, they are data agnostic.
It would be wonderful to test it. And we are more than happy
yes.
to collaborate.
Yes, we will be happy to test. Importantly, what we expect, we have the next week important AI, Universe AI in Athens.
Right.
That is, and we expect generative models, which we do believe that all of these tools that we have in astronomy ever developed to be imparted into generative models to uptake thousands and hundreds of the thousands of the papers to actually into the generative models to generate hypotheses, and then actually to apply all of these tools. Like in the Python now we have just simply AstroPy, Lomscargle. So all of these tools, the idea is that actually once again we have the AGN science, for example, collaboration generative model in maybe few years, or I don't know, and then the analysis will be completely on the different level, not on the level of, you know, making the codes. And
Thank you.
you're welcome. Yes.
So, how well can your software handle sparse and non-irregular data?
Yes.
Wonderful
Because
question.
LSST will be very regular, right?
Yeah. No.
Absolutely not.
Okay.
So that's, I mean, what people were, I can start, Andrika, that you can take over while you search the. So the first, let's say, what people were saying, like LSST is going to scan the whole sky every 3 days, but actually it's not that. The observing strategy of the LSST is much more complex, and it's let's say it's taking into account a lot of let's say aspects, and in different fields it's going to be different. For example, for us, for AGN studies, the so-called deep drilling fields are going to be super exciting, because these will have the largest number of visits, like tens of thousands. For example, the Wi-Fi deep is going to be about 1,000, and there are other avenues as well, and for even suggesting some micro surveys which will be incorporated into the whole survey. So there are different avenues to explore. So definitely it's not going to be regular cadence, but we.
Yes, here are actually examples of the application of
things.
the neural process on different type. These are actually kernel density estimates of the time distribution in our simulated light curves. And we can have how actually the LSST AGN data challenge based on the SDSS data from this central band is actually somehow spiky. It is not regular, and then we imitated the micro surveys, which we that have more frequent but shallower campaigns of few weeks just, and then we have completely, you know, ZTF that are not so nice, and you can see actually the points that black dots or points. They are the data in the simulated light curves, and you can see how we are actually across the bands reconstruct them and the transfer function. Importantly, in difference to the neural networks, we are not using the all light curves for learning. Just even we go more adversarial to just takes about some type of the number of the points in the light curves, not all of them. That is the difference. And you can see actually that we can even in such adversarial situation to apply. As for the QHX, because it is based on the wavelet transform, and we are using the wavelet Z transform to cross-correlate the wavelet matrices of the wavelet Z transform of the light curves, it can handle sparse data. It doesn't require the nicely spaced data, as you can see, for example, here in Gaia. You know, we can actually handle this data without any application of the pre-modeling step. So actually, we would like to go more in this direction, that we actually try to imitate human type of the learning, and perhaps that will be also one of the topic the next week. And even Kaggle, you know about the Kaggle, they announced a few weeks ago competition, I think $300,000 prize to make the generative model that will actually resolve their problem, which is logical, and to imitate human way of thinking. So actually, as humans, we have this type of nonlinear learning. And when we see, you know, somebody says, if I cannot see the period, then it means that it is not there. what we have in our human brain, we have nonlinear transformation.
And
That
we are
is-
very fast.
Yes, and we can see, you know, the forms. And QGX try to imitate this as well as the QNPy. But of course, we need, both of the software are actually open, and they are actually intended to support the community. People can use them, can, you know, destroy them, can build something new of them. And that is, you know, it is not like, you know, and that is in the line of the democratization of the science, which is the one of the main lines of the LSST and such big survey.
Thank you.
Thank you. That is important question. Thank you.
Can I ask the last question?
Yes.
So you said, oh, there's one more there.
No. Oh, sorry, maybe was there a question? No, it wasn't. Sorry.
So, you said you tried with the ZTF data, injecting periodicity in the actual
Yes.
Quasar light years. But have you tried just the periodicity set in the ZTF data without injecting? Without
Yes, it is
simulation?
here, for example.
Oh, so this is, and
Yes, without injection.
so have you done it in like how many Quasars?
It is about, you know, just thousands.
It's
Oh, okay.
Not
Not the entire
yes,
database.
not entire data, because we want to see how we are actually behaving, and then we actually intended, you know, but importantly, because our package requires that we have at least two bands, so we can do only
DNR.
And for example, we assume that the most of the information is contained in the, for example, in the LSST, in the U band as in the SDSS, and we are everything comparing with this. Here, we need to compare with the G band, but also we notice that there is a, if we have various surveys, then fine tuning of the statistical vetting is important, because not all data are actually the same. These are only like prototypes before. And importantly, we are not proving anything. We know in statistics, it is not, we will never prove anything. We can just say that our data supporting or against the hypothesis, and maybe the next data will say something different. And I think that that is important for our community to know that we are not proving, we are just we are extracting the evidence based on present data that we have.
That's what we want to do.
Yeah. That's why it would be really amazing, interesting to combine the efforts and
Yes.
test some different.
We know that Atom is devising wonderful methodology, and we are just, you know, we are open, because this due to going into higher dimension, it is more expensive, and it means that once again we have maybe, you know, sifted out with some faster code candidates, then we can go on the higher level of the inference, in sense to go into more details. And then, you know, because there are some other communities, like in the gamma ray, their pipeline devices are consisting of various types of the algorithms, and then they are applying the statistical hubs, uptaking from all of them, and then penalizing and judging about the robustness. So our codes are actually intended to be collaborative, to be cooperative with other. They are not adversarial to other codes. And that was in this study where we prototype, where we actually paired up the Lomscargle and our methodology. Firstly, Lomscargle had been applied on all of these SDSS objects, and then
SARP-82.
yes, and then we applied the QAJAX on the best in order to confirm with totally different, because it is more expensive.
It's more computationally expensive.
Okay. Let's thank you both again.
Thank you.